So another way we could find volumes using our integrations over one variable is through this disk and washer method. Now the washer method is a little more general than the disk method, but it's the same thing essentially, as we'll see in a second. Okay, and what you're doing here is rotating functions or a region around either the x-axis or the y-axis. Okay, and this is a little bit clearer if you see an image, which we'll show in a second. But the basic formula is this for the washer method. Okay, you have a function. You basically have an outer radius. So if you take a look at the area of a circle, it's pi r squared, right? And so here your f of x will be the outer r, and your g of x will be the inner r, and you'll get pi f of x squared minus pi g of x squared. Okay. Now the disk method is the washer method with g of x equals 0. So you just don't have an inner radius. So it's not really anything different. Okay. So this is what we'll get by rotating this region bounded by f and g about the x-axis. Okay. We could also rotate about the y-axis, and we'll end up with a very similar formula for rotating about the y-axis. Okay, and let's take a look at a concrete example which will help us better understand what this method is all about. Okay, so here we have this region in the first quadrant bounded by these two graphs. Okay, and we'd like to know which is greater, the volume that we would get if we took that region and rotated it around y, or rotated around x. Okay, and they're going to be slightly different, and so we should consider this more concretely. Okay, so we're going to get two different volumes depending on which one we rotate, either about x or about y. First order of business is to actually find where these intersect, and again you do that by just setting them equal to each other. You know, they're both equal to x here, and so we'll just set y cubed equal to 4y, and you end up getting that y is 2. Okay, so if you saw y is either 0 or 2, and if you find the corresponding x for y equals 0 or 2, it's, you know, the one that corresponds to y equals 0 is 0, and you could just use any basic formula there, and the one that corresponds to y equals 2 is x equals 8. Okay, so 0 and 8. So this point here is 8, 2. Okay, so x equals 8, y equals 2, and this point here is 0, 0. All right, well, let's first rotate about the y-axis, and let's take a look at how that looks when we do rotate about the y-axis. So here we see our region, which is bounded in the xy plane, and let's rotate that about the y-axis and see how that looks. So here it is rotating. Okay, now this is a volume, and you could see how we have a radius at a particular y there. Okay, so we're subtracting the outer and inner. Maybe that formula now makes a little bit more sense by taking a look at this visually. So since we're rotating about the y-axis and taking an integral over y, we're going to need all of these functions in terms of x in terms of y, right? So we'll have x is equal to 4y, x is equal to y cubed. And now the outer radius is this 4y, and so just using that formula here, you know, that's going to be our outer radius, py, and we're going to square that, 4y squared. Our inner radius is y cubed. You can see the inner radius there is y cubed, so pi y cubed squared. Okay, and so this will give us the sort of diameter of the washer. Okay, and we're going to rotate that washer around the y-axis. Okay, and when we do that, we get this integral. Okay. And so we just carry out the straightforward integration in y, and we get 512 pi over 21. Now, we could have rotated this around x instead of y. And let's see how that looks. So notice here that once we want to rotate about the x-axis, we have to be careful and write these curves as functions of x. And once we rotate, you could see we're getting the volume there. Okay, and so that's how the volume looks once we rotate it about the x-axis. And you could see the same dynamic there with the outer radius, inner radius. And you're getting a washer because you're rotating around the x-axis and cutting out an inner radius and just leaving you'll get the area of the outer radius minus the area of the inner radius shape. Okay, and so that's how this works when you're rotating about the x-axis instead of the y. Okay, so if we want to do that, again, we'll have to solve for both of these both of these curves now as functions of x. So instead of x is equal to y cubed, we'll get y is equal to x to the 1/3, and we'll get y is equal to 1/4 x for the bottom function. And the x to the 1/3 is our outer radius, our inner radius is this, and we just plug them in the formula. And here we have to also be careful, we're changing the bounds of integration from 0. Before we were integrating from 0 to 2 because we were integrating along y. Now we're integrating along x, and so we're integrating from 0 to 8. And once we integrate, we get 128 pi over 15. And so the volume that we get from rotating about the y-axis is actually greater than the volume that we get from rotating about the x-axis. And in here are both volumes computed. Okay, and so there's yet another application of finding volumes using integrals in one variable.